Hi there! Have you ever noticed how water seems to rush faster when it flows from a wide pipe into a narrower one? Well, it's not just a trick of the eye, but a fundamental principle of fluid dynamics governed by the continuity equation. Fluid flow is the volume of fluid that moves past a certain point per unit time. And it is mathematically presented as flow is equal to volume over time. Now let's discover how water flows faster through a narrow pipe. We have here a round pipe that serves as a conduit for some liquid, and suppose it varies its size along its course. So as you can see, the fluid here is moving from left to right. We'll take a long section of a narrow pipe here and we'll define the cross-sectional area as area 1 and the length of the section as L1. So as mentioned earlier, Q is equal to volume over time. We know that the volume of a cylinder is equal to its area multiplied by its height. So in this case, we have the Q1 is equal to area 1 multiplied by its length over time. We can also regroup this one, and length over its time is equal to velocity. Therefore, the flow from section 1 is equal to the cross-sectional area of section 1 times the velocity of fluid moving through the section 1. Now we'll define the section 2 and can quickly determine that the flow of the section 2 is equal to its cross-sectional area multiplied by its velocity. So the key concept here is that the flow of section 1, that is how much volume passes through section 1 per unit time, must be equal to the flow in section 2. And if these were not equal, fluid would back up somewhere and become very compressed. So for most liquid like water, density remains relatively constant or incompressible. Therefore, the equation simplifies to cross-sectional area of section 1 times velocity 1 is equal to cross-sectional area of section 2 times velocity 2. So this is what referred to as the continuity equation, a simplified form appropriate for non-compressible liquids. We can think of it as a statement of conservation of flow, which relates to the law of conservation of mass that is applied to moving fluids. Now let's have an example. A water treatment plant needs to deliver a constant flow rate of 1,000 liters per minute or LPM to a residential area. The main pipe leading to the area has a diameter of 50 centimeters, but due to a space constraint, a smaller diameter pipe of 25 centimeters is needed to pass through a certain section. Now we need to determine the water velocity in both pipe sections. By applying the continuity equation, first we must calculate the cross-sectional areas of the main pipe and the smaller pipe. So the cross-sectional area of the main pipe has the radius of 25 cm. So convert it to meter, then it is equivalent to 0.25 meter. Then area is equal to pi times 0.25 meters squared is equal to 0.196 meters squared. Now for the smaller pipe, area 2 has a radius of 12.5 centimeter. Then convert it to meter is equivalent to 0.125 meter. Then area is equal to pi times 0.125 meters squared is equal to 0.049 meters squared. Flow rate of the main pipe has 1000 LPM is equivalent to 1 cubic meter per minute. So note that 1000 liters is equivalent to 1 cubic meter. Then computation of the velocity in the main pipe, flow over area 1 is equal to 1 cubic meter per minute over 0.196 meters squared is equal to 5.1 meter per minute. Now let's apply the continuity equation to find velocity in the smaller pipe. Then we have the formula area 1 times V1 is equal to area 2 times V2. So 0.196 meters squared times 5.1 meter per minute is equal to 0.049 meters squared times V2. Then the cross-sectional velocity of our section 2 is equivalent to 20.4 meter per minute. For the results, the water velocity in the main pipe, which has 50 cm diameter, is approximately 5.1 meter per minute, and the water velocity in the smaller pipe, which has 25 cm diameter, is approximately 20.4 meter per minute. The continuity equation shows here that to maintain the same flow rate of 1000 LPM, the water velocity must increase significantly in the smaller diameter pipe. This critical information ensures that the pipes are appropriately sized to handle the increased velocity without causing excessive pressure loss or pipe damage.